Welcome back, everyone. So today we're going to talk about how we can relate our relative error of our Taylor series approximation of the exponential function to machine epsilon. And so how can we do this? Well, we're going to show that if we have x large enough and n large enough, this just means very large, then we have our relative error. Sorry, that should be a uppercase N less than or equal to machine epsilon. So we can get our relative error actually less than or equal to machine epsilon if we have n. I keep writing lowercase, I apologize. If we have n greater than e times x. This is not e raised to the x, this is e times x. And we're going to show this. And I should say that having this fact, so if the relative error is less than or equal to machine epsilon, this implies that we must have this. Okay. So let's prove this. Proof. So we already have that Rn is less than or equal to machine epsilon. Right? So we can simply just use our definition, or excuse me, our upper bound for our relative error that we computed in the last video. So if we have this, we must know that x to the n plus 1 over n plus 1 factorial absolute value must be less than or equal to machine epsilon. Okay. And again, this will just be equal to this. Oh, excuse me. Absolute value of x raised to n plus 1 over n plus 1 factorial is equal to machine epsilon. And this, we know this since, well, first of all, n plus 1 factorial, that has to be positive, so that's unaffected. And then, this must be true. The numerator must be, this conversion here must be true, since we're assuming that x is very large, which means it's much greater than 0, so it's positive. Now, what we'll do is, this doesn't seem intuitive, but it'll make sense later, I promise. So we're going to take the natural log of both sides, actually. And we really want to do this so we can split this quotient here into a difference. Because we know from the properties of logs that we can simply change this to ln of the absolute value of x raised to the n plus 1 minus the natural log of n plus 1 factorial. And this will, and the left side will remain the same. Okay, start the page. Now, from this, we can expand this further. We can use the property of bringing the exponent down to the front. So this becomes n plus 1 times the natural log of x. I'm gonna write that. I'm gonna get rid of that parentheses. Just make this absolute value of x minus the natural log of n plus 1 factorial. Okay. Now here, it seems like we have a little bit of a roadblock here because we can't really simplify this any further without any other identities. And that's where what's called the Stirling's approximation is going to come in. So I'll define the Stirling approximation. And remember, this is numerical and this is numerical methods. So approximately we treat as equals a lot of times when, we get a little bit sloppy there, but we're allowed to. So we have Stirling approximation. I'll do this for the general case. So the natural log of n factorial is approximately equal to n times log n minus n. I'll box that. So using this, we can simplify this term here, right? So what we'll do is we'll write that using the Stirling approximation minus ln. Excuse me. To write the n plus 1 term first. N plus 1 times ln of n plus 1 minus n plus 1. And this is still less than the natural log of machine epsilon. That looks like a zeta. Okay. So now we're going to note that we have ln of e is equal to 1. I'm going to make this separate. This is going to seem very odd that I'm doing all this. We have ln of e is 1, right? We also know that ln of ab is equal to ln of a plus ln of b by the properties of logarithms. So we know that the natural log of e times the absolute value of x must be 1. Oh, let me write it out a little clearer. The ln of e plus the ln of x is equal to 1 plus ln of x. Now, why is this useful? Well, let me write this. Oh, actually, I have more space here. Perfect. So this is useful because we can note that we have n plus 1 times the natural log of e, is the absolute value of x, is equal to n plus 1 times 1 plus the natural log of x. So this means that this quantity here is equal to n plus n times the natural log of the absolute value of x plus 1 plus ln of x. When we expand that out, and we could simplify this further to n plus 1 times ln of x plus n plus 1, right? So when we use this replacement in the inequality stated above, you can see here, we have this quantity here. Did I make an error here? Yeah, I did. This should be plus. I was wondering why. Okay, let's go to the next page. So plugging that in for our term here, we can see, going back, these two terms here. Oh, wait, whoops, that's too high up. This term here, and this term here are both included right here. So we can just simply plug in this here for those two terms. And we're left with the following. So we have, go back here, n plus 1 times ln of e times the absolute value of x minus n plus 1 times ln of n plus 1 And this is less than or equal to the natural log of machine epsilon still. And we can also distribute this out. So we have ln of ex, ln of e times epsilon of x minus natural log of n plus 1. Cool. You're probably looking at this now and you're saying, okay, that's all great, but now what? Well, if you remember, machine epsilon, this is a very small number. We're talking hundreds of digits past the decimal point. And maybe, I don't know, 2 there, I don't know. Whatever it is. It varies. But this is a very, very small number. And the natural log of a very, very, very small number, meaning between 0 and 1, that'll be negative. So that means that this is less than 0. And so if this term is less than 0, this term must also be less than 0. So we can conclude here that we must have that the left side of this equation, of this inequality, must be less than 0. And this is nice because we can just simply get rid of that n plus 1, and we're left with natural log e times the absolute value of x minus the natural log of n plus 1 is less than 0. And then further, just add that to the other side. The natural log of e times the absolute value of x must be less than natural log of n plus 1. And taking the exponential of both sides, if e times the absolute value of x is less than n plus 1. And finally, remember, we assume that x is very large. Whoop, that's the opposite. X is very large, and also n is very large. So since we know that x is very large, you know that x is equal, the absolute value of x is just equal to x. And in this case, we're going to assume that n plus 1 is approximately the same as n, since n is very large. If we're talking about super large numbers, let's say like 220 or something, well, we're going to consider that approximately equal to 221. Okay. And when we do this, we're left with our result that e times x is less than n. And this is exactly what we wanted to prove. So going back to our original thing here, so we now know that if our relative error here is less than or equal to machine epsilon, then we must have e times x is less than n. And that's a nice little proof. So this video and the last video have really just been trying to understand what the bounds look like for approximating the exponential function. And in the next video, we're going to actually write some code to approximate e and see how it does for some range of values of x. And we're going to just look at the results and see what our relative error looks like. Excuse me, what our approximation looks like in comparison to the analytical definition of e. So thank you all for watching. I look forward to seeing you in the next video.